I'm retired manager of the HPC part of the GWGG, and as such, I'm a predecessor of Professor Kunkel. So I'm happy to be here. Since my retirement 11 years ago, I continuously gave courses on parallel programming with MPI. So I'm happy to do this in this course also. So we have here in the schedule things I will cover. And you see, you can reach all the slides, the presentations I will use from this sheet. You can read them on your screen also. So the MPI part is in several sections. I will start with the basic principles of parallel computing, where I will probably have some overlap with the things Julian Kunkel gave you yesterday. And then I will continue to give the general introduction to MPI, and then start with exercises to use MPI in practical examples. So we have just this running and compiling MPI programs, and then we will cover the essential points of MPI, the point-to-point communication and the collective communications. And these are the core properties on the core functions of MPI, the communication of point-to-point and collective. Then I have three applications where I will show how to parallelize a sequential program and which steps one has to use and how one can use the properties and the functions of MPI to parallelize them. So we will have these points today and tomorrow. And you see there are some times scheduled for all these parts, and we'll see whether we can stick to this schedule, or perhaps we have to be flexible and change the times some way. But I will try to stick to the starting times in any case. So let me begin. Oh, I have to load now the tutorial by the presentation for the parallel computing. Okay. I think I will now switch off my my video so that the slides are in a bigger format. So just this. Okay. So what is the basic of parallel computing? The definition in Wikipedia for parallel computing is written here. The computation in which many calculations or the execution of processes are carried out simultaneously. So now we have to ask, why do we need this? And then we ask, how do we do it? So the things I will cover here are the following. Why do we do it? It has to do with the evolution of computing power. And then how do we do it? We'll cover some explanations of where parallelism in hardware can be realized, and then how we have to worry about communication and data dependency. And then we come to the questions, how do we program the parallel hardware? How do we tell the hardware what to do in which order? And very importantly, how do we assure that our parallel program really is efficient and doesn't lose too much time in communications and so on. So let us begin asking, why do we need computing power in the first place? So yesterday also already Julian Kunkel explained in which fields we need computational power. So in all the cases, cosmology, climate engineering, and so on, drug design, elementary particle physics, that's the field where I'm coming from and I'm interested mostly. Or in analyzing huge data sets which come from experiments or from observations, which again are in particle physics or in the genomic biology, or analyzing the internet and so on. So for all these purposes, we need very much computing power. The more we have, the better. Now, where does computing power come from? The definition of computing power for us will be just the number of floating point operations per second, which can be delivered by the system. So it's measured in flops, floating point operation per second, or because one flop is very slow, we have the kilo, mega, giga, tera, peta, exa, always a factor of 10 to the 3 more than the one before. So this is the that's the measure of computing power. And now, what on which factors are the computing power depend? Depends on the number of computing elements in the system, of course, proportional to the number of computing elements, and the number of circuits involved in one floating point operation. So one circuit takes a certain time, so if one floating point operation needs n circuits to do its job, so we have the computing power multiplied by the inverse of n. And then, of course, we have computing power multiplied by the frequency, which is 1 over the cycle time. So we have this formula for the computing power, and the important point are the number of computing elements we have, and the more computing elements we have, the higher the computing power will be. And again, also the frequency, the speed, the clock speed of the circuits will determine the computing power. The higher the frequency, the higher the computing power. Also, if we want to have more compute power, we can increase the frequency, or we increase the number of computing elements. The frequency has increased over the years. We have here an evolution of microprocessors over the years, and different properties of the microprocessors, which is here the number of transistors per microprocessor, which is increasing exponentially all over the time, which is due to the technology which makes the size of the circuits smaller and smaller. So you can pack more and more circuits onto the same area of the die. But you see the frequency is not increasing anymore since about 2002 or 4. frequency of the operation of the circuits is staying constant. That is due to physical properties. The heat which is generated during the execution will increase, and you cannot extract the speed, the heat fast enough, so it's not feasible to increase the frequency anymore. But since the number of transistors are increasing, you can just pack more and more logical cores into the same chip. The number of logical cores will increase also. This is the number n, which is increasing, but no longer the frequency f is increasing. This was formulated as a law many years ago, the Moore's law, which said that the number of transistors in integrated circuits is increasing exponentially, doubling every 2 years. And this is still the case because the technology has not reached its limit, but which is not Moore's law, but which was in the beginning proportional to Moore's law, that the clock rates get faster and faster. But this is since 2003 not longer the case, so the clock rate is staying constant. But nevertheless, because of the number of cores can be increased, we have an increasing power of the fastest supercomputers in the world, which is collected in the top 500 list, which is generated every year to collect all the fastest 500 supercomputers in the world. You see this number is increasing from in gigaflops, so we have here now gigatera beta exaflops. You see the blue is the sum of over all 500 supercomputers, and the red is the fastest one in the world. And you see the red is a stepping curve, because it costs very much money to build such a fast computer, and if it's put in execution, it will be work for some times, and it will stay the fastest because the next one takes some time to build the next one. So at the moment we have the fastest one here in Japan. So you see the computing power is increasing, but not due to the increasing of the frequency, but due to the increasing of the number of cores in the system. So what do we conclude? We have a single compute node with many cores on a die on one chip, have number of computing elements in the order of 10, but the clusters which combine many nodes will have about in the number of order of million computing elements. And if you want to use these computing power of nodes and clusters for complex simulations, and you can do it, but then you need parallel computing. That's the last reason, the deep reason for using parallel computing, that the computing power depends on the number of computing elements which you want to use simultaneously. Okay, but what are the conditions to use these many numbers of computing elements with parallel computing? You have several things to consider. You need to have the parallel hardware, which I will describe in a moment, and you need to have your problem to be parallelizable. You need to have parallel algorithm which can use different steps in parallel. And then, of course, you have to use software to map the algorithm to the parallel hardware. So we have to discuss parallel programming languages. And then we have to consider what does it mean to have a high efficiency, because the parallelism to coordinate many processes in a common algorithm needs some coordination, and this can reduce the parallel efficiency, and we'll discuss this. Now, first we will discuss in which way the parallelism can be built, maintained in the hardware. We start just at the core of the hardware, the processor, and a processor can be described as with two parts. It has a memory and a central processing unit. And the central processing unit, again, consists of some instruction unit and the unit to do the arithmetic or logic. And it has to have the data which are written in the cache or in the registers of this CPU. Now, the functional unit here can have several pieces. It can have not only one, but several functional units for addition and multiplication and other purposes. This is also, there's a parallelism in the number of functional units. And each functional unit to do a multiplication can be also parallelized, can be split into several steps to split the operation of the multiplication, for example, into several steps. And for each step of this multiplication, you have a separate circuit. And so you can do the multiplication on several operands at the same time with several different steps at the same time. So the first operands can be worked on in the last step, and at the same time the next operand can be worked on in the last but one time, and so on. That's just as a factory line for pipeline in the car manufacturing also. So we have a parallelism in the execution of a numerical operation, which means that if you have many similar operations to do one after another, you get a result every time one of the segments can operate, which is just the clock speed. So each circuit for this is done in one clock cycle, so you get one result at every clock cycle. If you can use this multiplication pipeline, if you have enough multiplications to do one after the other. Finally, you have the data you are working on are floating point numbers, and a floating point number consists of many bits, so typically double precision 64 bits, and you can manipulate all the bits at the same time using this 64-bit chips architecture. You see in the 70s or 80s, you had the first personal computers which were, I think, 16-bit, which was a great advantage about the former computers which could work only on one bit at a time. So, and then the parallelism in the bits increased by time and over time, and now we have parallelism in bits in number of up to 512 bits. So you can do a parallel with 16 parallelism with 16 floating point numbers at the same time. So this is the deepest level of parallelism in a processor element. Here I have again collected the steps, the levels of parallelism. You have the bit processing, you have the pipelines, and you have multiple functional units. These are the parallelism which is inherent in every core you use in today's computers. So if you think of a typical computer of today, a node of today, one core will do 4 double precision floating point operations because it has 4 parallel functional units per cycle time. And every cycle you can produce one result in at each of these functional units. So if you have a cycle frequency of 2.5 gigahertz, you will get 4 times 2.5 gigahertz, 10 gigaflop per second, which is the typical maximal speed of today's cores of today's computers. So you can go at a higher level just to use parallelism at a higher level with multiple computing elements. This was just one core, one computing, one CPU, but you can now use several CPUs at the same time. And the most simple way to use it is that you have one instruction on your instruction unit and do the same instruction for different operands from the memory. So you have many large number n of functional units, which every one can do a multiplication, say, and then you have here instruction to do a multiplication and can do multiplication with on n elements at the same time. So that's a parallel scheme which is called SIMD, single instruction stream with one instruction unit, but multiple data streams. You have multiple functional units to do multiple data operations on multiple data at the same time. This is a way which is, of course, used in for example graphic processors where all the pixels of a screen are worked on in parallel. Then you can do parallelism at a higher level with multiple computing elements. So you have several full CPUs which have instruction unit and functional unit. And you can use several of these types and combine them with a memory to use a common pool of data. This is a kind of parallel computing which is called MIMD, multiple instruction streams and multiple data streams. Every instruction stream will have every instruction in this stream, in one stream, will have its own data. So you can use this in 2 different ways, that you have your CPUs attached to a common memory, so that every instruction stream will fetch data from the same memory, or you have a system where you have full processors including CPU and memory, and every CPU has its own memory, and they are connected by a network interconnect. So this is typically a multi-core processor, which your home computer will have, your desktop computer will have, and this is typically this thing which you will find in computer centers, where you have large clusters where which are composed of very many CPUs which are connected by a fast interconnect. These are the two types of higher level parallel computing. And of course, in the real life, you will have a hybrid system where you have a cluster of shared memory nodes. So in this case, where you have an interconnect and every part you interconnect is itself a shared memory multiprocessor, which is indicated here. And this is the way the large clusters of today are constructed. Now, of course, you have to worry about the interface to to communicate data between the different computing elements. And in shared memory system, you have to interconnect different CPUs to a common memory. You can do this by a bus, so that every access to the memory is serialized. Only one computing element can access the memory at a time. So this is not very scalable, but it has it's very fast because you can switch very fast over a bus to the memory, to different locations in the memory. And in order to improve the scalability, you can also partition the memory in different pieces and have a cross link between the processing elements and the memory elements, and so every process can access simultaneously different part of the memory. But of course, if all processes, all CPUs want to access the same part of the memory, then again you have a bottleneck. And of course you have a larger latency because you have to use a switching interface here. And the same similar considerations have to be taken for the interconnect of full nodes. You can interconnect them by a switch, that every node can access every other node at the same time. So that's the most fastest and the most expensive part, kind of interconnect, if you have a connection of every node to every other node. The cheapest one is just a tree, so that every node is just connected to two other nodes, and so in the end you can get from one node to the other node either in one step, or if you want to reach this, so you have to do 2 steps and so on. And in intermediate level of interconnect would be a torus or a grid, where you have an interconnect of every node to some neighbors. So the number of neighbors correspond to dimensionality of the grid. This is a 2-dimensional grid here, but you also have higher dimensional torus grids. So what's important to know about the network? There are 2 numbers, which is one number for a network operation is the latency. That is the time which will be taken to set up the connection between 2 nodes cluster. That is the time, how long it takes for the first bit you want to communicate to reach the destination. Depends on the kind of interconnect, which has to, if you want to connect 2 nodes, you have to set up a communication path in the hardware of in the connecting hardware. The latency. If the communication channel has been established within the latency time, then you can start to communicate data with a certain speed, which is the bandwidth. inverse of the bandwidth. So C is the rate of data, the number of bits or bytes which we can transfer per second. And of course, if you want to communicate a small set of data, then you have every time you have to set up the latency, and then you can start to communicate the data. But if you have to communicate large sets of data between the same endpoints, then you can you need only once to set up the communication channel, and then you can communicate the data with the communication speed, with the bandwidth. So you have an effective bandwidth, which is the nominal bandwidth times the number of data, latency times C over the number of data. So these are the main parameters for the network to be considered. And then with respect of parallelism, you have to worry about the bisection width, which means how many connections can you use at the same time. So how many connections is your interconnect provides for connecting different parts of the net of the nodes connected by the network. So what is the relevance of these network parameters? It's very easy to see. If you have attached some processors with a certain compute power R to via a communication network with the parameters latency and bandwidth, you can see that the product of the latency times the communication times the computing power is just the number of flops which could be executed during latency. So that's the number of flops you use for establishing the communication path. And then the number R over C times 64 is the number of flops which could be executed during the transfer of one floating point number. The number 64 is because C is measured in bit per second and R is measured in floating point operations, which are 64-bit numbers. So these are the typical parameters which are relevant for your application. We'll see an example later on. So this, let's see how large these parameters are in some realistic cases of the cluster. We have, for example, at DWGG cluster, we have single nodes of the Intel Broadwell type, which have a latency of 0.2 microseconds and a bandwidth of about 64 gigabit per second. So, and the computing power for one core in this node is just 8.8 gigaflops. So the number of floating point operation could be done in the latency time about 2000, and the number of floating point operations which could be done in the time one floating point number is communicated would be 9. Well, same is a more modern node, Intel Cascade Lake. And then we come to the cluster where we have full nodes combined by a network. This InfiniBand or the omnipath network have typically latency times of 1 point something microseconds, and bandwidths also in the order of tens of gigabit per seconds. But in this case, you have to communicate between nodes, and the nodes consist of many cores. So if you extreme example is the Cascade-like nodes have 96 cores, so you have a computing power of one node for 880 gigaflops. So if you combine the effect of the latency on this computing power, then you have a great loss of floating point operations. 1 million floating point operations could be done in the time one communication channel between two nodes is established. And the same for the number of floating point operations which could be done during the time one floating point number is communicated, which is nearly 1,000. So in order to use efficiently these kinds of clusters, you have to worry very much about the amount of communication which is done during your computation. So some examples which you also saw yesterday in Julian Kunkel's slides, or similar one. The first massive parallel computer in the 1980s was the connection machine, which was very famous at this time, which had an interconnect 12-dimensional hypercube. So every node was connected to 12 neighboring nodes, but every node was only a 1-bit processor, 1-bit core. So it could do floating point operations, but it had to combine 64 bits, 64 cores to do one floating point operation. So the maximal speed of this large number of cores was just 20 gigaflops. That's the same speed today notebook of today will reach. It was the most advanced computer at this time. Now, today's top is one of the in the US, the fastest supercomputer is an IBM system, which is composed of nodes, of IBM nodes, which have 22 cores each, and a very large number of GPU, which also were mentioned yesterday in the talk of Julian Kunkel, which are graphic processors. So if you combine the computing power of these things, you get a maximal speed of 146 petaflops. And again, this is a fastest computer of today, which is in Japan, and it has 460, which is built out of nodes of the ARM so now let's think a little bit about the memory hierarchy in such a computing system, in a parallel computing system, and the effect of the communication speed. So typically, you have a hierarchy of memory in your cluster. You have a cluster of nodes, and every node has a main memory, and this main memory serves a number of cores, and every core itself has a cache and registers and functional units. So this is the memory of the memory hierarchy of today's clusters. You have the cache, and then the local memories of the nodes, and then you have the connection between these local memories. Now, the speed of the memory access depends heavily on the location of the data you want to access from your CPU. So the CPU can do 4 operations per cycle if the data are residing in its registers. So the cache is rather fast, so you can access 2 words per cycle from your CPU. You can feed 2 words per cycle into your CPU, and if you reuse the registers, you can just maintain this speed for operations per cycle with data lying in the cache. But already, if the data are not in cache but have to load it from local memory to cache, you will have a access speed of about 0.1 words per cycle. So it's a factor 20 less typically than accessing from the cache. And again, a factor of 10 less if you have to access the data from a different memory, from a different local memory, so you have to access them via the distributed memory. What does this mean? If your data you want to operate on are located on a different local memory, you will never reach these 4 operations per cycle. This is the rule for data access. Maximal computing power, which is just defined by the clock rate times number of CPUs times number of operations per CPU, can be realized exclusively for operating on data in cache. That's a very important rule. All other cases, you will lose computing power due to memory bandwidths. We will see this in a moment in the example how one has to consider this rule. Oh yeah, in this example, I will give you an example. Yeah, how this memory bottleneck affects your algorithm. Consider the memory access patterns for matrix multiplication. If you want to multiply 2 n by n matrices, then you have, in order to calculate one result, you have to calculate the dot product of a row times a column, which is just 2n operations. So in order to calculate all the elements of your result matrix, you have 2n to the cube operations. Now, imagine that you do this in the following order. Just calculate the results in one column, and for every element here you have to read from memory one row and multiply it by the same column. So, but if you want to calculate all these results, you have to read the full matrix into your from memory into your CPU. So you have, to calculate one column, you will execute 2 n square operations, and you have to read n square data from memory. So, and if n square times the size of the numbers you work on is larger than the cache size, then you have to reload for the next column. You have to reload, or even within one row, you have to reload the data into the cache. You have the data no longer in cache. So this will slow down your algorithm by this memory access program. So what you could do is not just calculate one row, but one block. Block has B size rows and columns, and in order to calculate one block, you have to do B size to the cube operations, but every time you have in your cache, you have to only to load B size square data. So if you choose the size of this block accordingly to the cache size, which is if you use this B size square smaller than cache size, then you will be sure that you can do the multiplications out of cache, and you will not be slowed down. So that's a way algorithmically to avoid this data bottleneck. Okay. Now, come to discuss what does it mean to have a parallel algorithm? How an algorithm must be tailored to be able to use simultaneously different hardware parts, different hardware functionality. So we have a very simple example, a vector addition. So all the input data are independent from each other. So in this case, 4 cores can do this vector addition simultaneously because every core can access different data and produce a result. So you have no data dependency in this case. Another example is if you want to do a sum over all elements of a vector, you of course cannot do this simultaneously with 3 or elements, but you have to have the result of one operation before you can add the next one. But you can do it in a clever way to just do the addition of independent elements at the first time. So in this case, you can do 2 sub additions, and then the next step to do the partial result, the adding the partial result. So you can do a reduced kind of parallelism. And if you have n elements, you can do it in not in one step, but in log n steps. And an example where data dependency prohibits totally the parallelism would be generating random numbers, which where the new generated number depends on the last number times a multiplication modulo sometime some modulus, which is the algorithm for producing random numbers. So you can do this only one number after the other. So directly you cannot parallelize generation of random numbers, but there are clever algorithms to do it nevertheless. But these are the considerations about data dependency which have to be done for every parallel application. Then we have the type of parallel algorithms which depend on the amount of dependency between different parts of the algorithm. We have the embarrassingly parallel algorithm, which just is a simultaneous execution of independent tasks. So you need no communication between the tasks, so you can do it just simultaneously, and there's no problem. Next example would be a simulation of extended domains, which is a problem occurring very often in application, technical, physical applications. If you have some domain, in weather forecast, you have the atmosphere domain, then you can split the domain into subdomains and calculate the temperature and so on in each subdomain. But on different processes, but of course the subdomains do border each other, so you have a connection between the subdomains, and the values in one subdomain calculated in one subdomain are needed in other subdomains, in the neighboring subdomains in the border. So you have to communicate the results of boundaries. It's a typical example. And third example would be algorithms for data fields, for matrices. Then you can the field into subfields, and these fields are mapped to different processes, and every process manipulates data from its subfields, but usually it has to use data from other fields to do these calculations. So we a kind of algorithm where the data fields are mapped to different processes. We will find in an application also this case of parallel application. We had already a system. Okay. Now, the programming models. Now we come. How do we tell the hardware what to do? We have to use some coordination of the instruction stream and data stream, and this is different for different kind of parallel systems. If we have shared memory, then we have all data in the common memory, and we have only to distribute the instructions. We have to tell every process which instructions should be done on this process. And of course, we have to synchronize the access to data in the memory, because in memory is shared. For distribute memory, there's more work to be done. For parallelizing, we have to distribute the instructions to processes, but also the data, because the processes have their own memory, and so we have to distribute the data to be worked on the different processes, and then we have to communicate between different local memories. And according to these two different types of memory organization, we have two different programming models: the shared memory programming model and the message passing programming model. And I will discuss this principle way to this programming model are constructed. We'll discuss by comparing them to the sequential processing model, which is the von Neumann model, stored program model. So in the sequential model, you have some memory, and you have the CPU, which has an instruction unit and the arithmetic unit. Of course, you also have input and output parts of the model, but I don't discuss them. I only discuss memory, and in this model, you have the memory, which contains the data, the instructions, and a program counter. And you have the CPU has an instruction unit and an arithmetic unit, and the instructions have the structure. You have an opcode, which tells you what kind of instruction has to be done. You have the operands and the address of the operands, and you have the address where the results should be put. So the way the program is executed is, you look at the program counter, where you have the number of the instructions. These instructions are numbered consecutively, and you look at the program counter, which which instruction number has to be instructed. Then you fetch this instruction and feed them into the instruction unit. The instruction unit decodes the instruction as to this opcode, and it tells the arithmetic unit to fetch the operands from the indicated operand addresses, to do the operation, which is indicated by the opcode, and to store the results to the data. And the order is sequential. That is, the next instruction will be executed only if the result has been safely stored into. So that's the general rule, but the important property of this kind of program is that the instructions can also include addresses which relate to the instructions themselves or to the program counter. So you can have an instruction to raise the program counter by 2, which is a jump in your program. Or you can have an instruction which says that the next instruction should use an operand which is just eight bytes away from the first one. So you can do loops with this kind. So because the instructions and data are in the same memory and are reachable by the opcodes in the same memory, you can do a very general way of computing with loops and jumps and so on. That's the sequential way. So the shared memory way of doing the computing. You have again a memory with instructions and data, but now you have several CPUs with instruction and arithmetic units, and you have several program counters, one program counter for every CPU. So in addition to the data and instruction, you have the local program counters, and you have the numbers of the different cores of the different CPUs, which are the thread IDs. So then the instructions are the same as in the sequential model. You can do everything and modify program counters and instruction and so on. But of course, you have to be careful that you do not write data at the same place at the same time from different processes. So you have to have atomic operations. And what you have to do in your program just to organize that the instruction to different are mapped to different streams, which you can do using the thread ID of every the synchronization here is that you have atomic operations, which means that you have you can read data simultaneously from different CPUs, but you can write data only at one time from one CPU. If one address is written to, then this address cannot be accessed by different CPUs. And this is a kind of synchronization you can use to organize your program. Finally, the message passing type of programming model has several memories, different memories, and different CPUs in a communication network. And in addition to the instructions, data, and program counter in local memory, you have in every local memory a receive buffer. And the operations are not only the usual operations to do on data in the memory, operations, multiplication, and so on, but you have also an operation which is send data and receive data. So you have every CPU has a unique task ID, and you have operations which tell you that is send operation, that the CPU should send data from some place in its memory to the receive buffer of a different task ID of a different CPU. So you can say send some value of content in your memory to a receive buffer of a different process. Of course, then you have in order to use this data, you have to receive this data. So you have also an operation receive data from your receive buffer and put them into some memory place in your own memory. You can also indicate from where the data have to be sent. So this is a kind to communicate data in two steps by sending them to a receive buffer and receiving them from the receive buffer. The synchronization is done in a way that the receive is blocking. So if you have an instruction in your counter receive data, them into some place, you will only can continue your program if there are data have been written from the other process to your receive buffer. So this is a synchronization way. This is the abstract model for message passing, and we will see how message passing interface will use this model in its definitions. Now, I see the time is 11 o'clock, but I will just continue for 10 minutes to finish this general introduction because we will have enough time later on. Which languages do we use to implement this programming models? General way is to use an established programming language, Fortran, C, C++, Python, or so on, and to augment this by language constructs. So for the shared memory programming model, we need a construct to create and coordinate threads. And this is done either with POSIX thread library or with OpenMP, which is the abbreviation of Open Multiprocessing. This is for shared memory programming. Message passing programming model must create and coordinate tasks and must give the possibility to communicate data between tasks. This is done in the message passing library. And then there's also the SEMD programming model for graphics processor, which is, for example, the CUDA Compute Unified Device Architecture for graphic units, which I will not discuss here anymore. Let me see. We will in the sequel, in the next parts of this course, we will detail just the message passing library. But for the moment now, I just want to spend a few minutes and last minutes on the efficiency of parallel computers. Again, we had the power as the number of processors times the number of steps to number of floating operations which can be done in one cycle times the inverse cycle time. And if we just look for a number, the cluster, the GWDG cluster AMP consists of 92 nodes, which each 96 cores. So we have a total of 8,832 cores, and each functional unit, each core can do 32 operations simultaneously, and we have a frequency of 2.3 gigahertz, so we get at the maximal speed of 650 teraflops, which is a giant number. So, but unfortunately, this number will never be reached because we have some sources of reduction of the efficiency. And let's see, the single processor efficiency, which is of course reduced by some problems concerning memory access. If you have data not residing in the cache, then you don't reach the expected efficiency. And then if you cannot use pipelines very efficiently because your vector lengths are very small, and the pipelines cannot be used continuously, or if you don't use your parallel pipelines at the same time. So you will have reductions of the single processor. But what for us, for our concern is now the parallel efficiency. So we have three four sources for reduction, which is the sequential parts of an application, the load imbalance, the communication of data, and synchronization, which I will shortly describe here. So normally a sequential application has three phases: data preparation, transformation of data with operations, numerical operations, and the extraction of results. And usually you can parallelize only the operations in the middle part. So if you have three functional units, three elements to work in parallel, you will do the first, the start and the end phase you can do only on one process, but you can do the transformation on three. So you have the execution time is the initial and last time plus the application time over three. So this can be has been generalized by Amdahl in the 60s of the last century, which gave rise to Amdahl's law. If your application has n operations, out of which the sequential operations cannot be parallelized, but these number NP can be parallelized, you will have an execution time of tau, is the execution time for one operation, times ns plus np over p, because this can be done in parallel on P processors. So on P processors you will have this execution time, the percentage of parallel operations, percentage of sequential operations. So of course, if you want to calculate the speed up, which is the number of operations, the improvement of your computing speed, which is the time for one process over the time on P processes, which is then P, the number of processes. This is the best result you could achieve, but it is diminished by 1 over 1 plus P minus 1 times sigma, the part, the sequential part. So if for the same program, for the same size of the program, the number of processes you use is rising, so you will get a speed up which is at most 1 over sigma. So you have a border of the parallelizable. The same for the efficiency, which is just S over P, which is in the best case efficiency is 1, but you have diminished it by this factor 1 over 1 plus P times sigma. An important number then is which sequential part you can afford to have still a 50% efficiency, which is just sigma 1/2 is 1 over P minus 1. So for our example for the GWGG cluster with over 8,000 processors, you have a sequential part you can afford to have still a 50% efficiency would be so about 1/10 per mil. Very smart. So this, you have to keep in mind that number of processes you can use meaningfully is limited. Same is if your application is distributed in an unequal way to the different processes, so then the total execution time will be dominated by the largest, by the processor with the largest processor time, of course. This can be also generalized. Go into it. Now, the third reason for reduction is the communication. So if you doesn't have a embarrassingly parallel program where you just have to distribute the operations on the different processes, but you have intermediately to communicate data between the different parts of the operations of the algorithm. Then you have communication time, and of course the communication time may depend on the number of parallel processes. And finally, you have synchronization. If you want at some point of the program to wait for the completion of all partial results, then you have to synchronize all processes. And if you want to establish a synchronization, you have to contact every process. So if deep processes, then you have to establish a communication with every process, which is proportional to the latency. So typically it would be proportional number of processes times the latency, but you can improve this if you synchronize in a cascade manner, then you only have the logarithm of p times the latency. In any case, you should do synchronizations only in large time steps, which are such that the computing speed times your granularity over p is larger than the synchronization time. Now, just to exemplify the communication load, in one example, again, the matrix vector multiplication, typically you would distribute your matrix on available processes here, two processes in a in a row block fashion. You have one row block on process 0, process 1, and process 2, and also the input matrix input vector is partitioned, is available only on the different processes. So if you want to put the result for every for all elements, then you have at first on process 0, you have at the beginning only the part, the local part, so you have to communicate the other parts from the other processes. So you have every processor has to communicate the input elements from the different other processes. So every process has to calculate n over p elements of the result vector, which means it has to do n squared over p operations, but it has to receive np over p elements from each of the remaining processes. The total time is just the computation time, which is the inverse computational power of one processor, times the number of elements to process, and then the communication time, which is p minus 1, times every communication needs a latency, and then the word bandwidth times the number of words to be communicated. So the efficiency will be diminished by two parts, which is one part coming from here, from the latency, which is multiplied by p square over n square, and one part is diminished by the ratio of computing speed over bandwidth times p over n. These two factors should not be too great to maintain a meaningful efficiency. So let's say it's a good efficiency that both factors are smaller than 1. And then we compare this with the numbers we had for our cluster, the lake intercluster, where we had this number is 1 million and this number is about 600. So we get some bounds that the number of elements, number of rows and columns of our matrix divided by the number of processes should be about 700. So you see the communication parameters will limit the number of processes to be used, meaningfully to be used in such a calculation. This ends my introduction of on parallel computing, and if there are some questions, I'm happy to answer them, and otherwise I will continue, say in 5 minutes, to have a short break. I will continue at 11:25 with the introduction of the message passing interface. Okay, slide 30. Oh. Okay. You want to calculate the Bn square elements of this block, the result matrix, and to do so you have to multiply this block of the input matrix A times this block of the input matrix B, and add them to the result of the product of these red blocks, and so on. So you have, in this case, if you have just 4 blocks, you have, in order to calculate this one block, you have to do 4 block multiplications. And for every block multiplication, you have this consideration that the block size, if the size of the block is smaller than the cache size, then you will use for this number of operations only this number of data. I hope this answers your question, or? Well, if you implement it, you have to write it in some programming language, say Fortran, and you would have to write do loops over the block, and just as in this case, you have to do loops over the blocks summing the products of the relevant elements of the blocks in the input matrices. I think the answer to row when speed ups are meant by using both a clever way to data in memory to access them fast in cache, and to the SEMD SEMD ways of the modern hardware to use pipelines. Okay, so that's the pipeline. Well, as to Mike, here we will come to it in a exercise session, and then we will try to see what it's like. But I have given permission to all these folders, so you should not be problems. I don't know why. Okay. Just a short moment. Okay, I would like to continue now. An introduction to the message passing interface. Just remind you, the message passing interface is a realization of this abstract programming model for message passing, where you have the send and receive operations in addition to the normal opcode operations of your sequential programs. And you have to manage receive buffers in addition to the data and instruction. Now, why do we need, what is interesting to have a message passing interface? The reason is that in the last decades of the last century, the desktop computers were available and abundant, and people wanted to connect them and to try to use them in parallel. And in this time, a huge number of different software was written to just to create a parallel environment for these collections of computers. So that many people wrote programs to to use parallelism in for these nodes, and it was not possible then to use this program on different hardware, because every hardware cluster used a different way of combining and communicating with each other. A large number of things which are very elaborate, and then people, users and manufacturers came together and said, well, we have to find a common language, a common interface, so that we can reuse our programs on different hardware. And so the MPI, the Message Passing Interface Community, was founded and created the first standard in 1994. And this effort is continuing up to today, and generated upgrades and new versions. And today, as of 2010, we have MPI version 4. It is a very great effort of the community to have a common framework for message passing parallelism. So what is the meaning of message passing interface, MPI? What does it contain? A long way, it's the message passing library interface specification. MPI stands for Message Passing Library Interface Specification. So first place is a message passing. It is a realization of the message passing programming model, which is data exchange between different processes. But it has many extensions. Collective operations, one-sided communication, process control, and parallel I/O, and so on. So it's a add-on to the bare message passing programming model. And it's concerned with message passing, and it's a library. So the operations are invoked by calls to routines from a library. So you can use it from a usual programming language by calling library routines. And very important is an interface specification. So MPI specifies the calling sequence and the intended result of the routines in a language independent manner, and it also specifies the binding of this specification to Fortran and to C. That is the end of the message passing interface. Of course, they are binding to other languages, but they are not in the MPI standard, but they are add-ons. Most importantly, it's not an implementation. That's very important, because you want to use your program written with the MPI to use on different hardware realizations. So, and these different hardware systems have different kind of interconnects and different kinds of interconnecting hardware. So the hardware manufacturer should, or the community should, provide implementations for different kinds of hardware. That's not that's not a thing the user has to worry about. The user only has to write his program in a way conforming to the standard Mpi standard, and then you can be sure that this program will run on all systems which have an implementation. The implementation is not in the realm of the Mpi system, but has to be done by different communities. Excuse me. So the general setup for parallel processing for Mpi is that a program consists of different autonomous processes or tasks, and every task executes in its own code, in its own memory. So the MD style, because you have autonomous processes executing simultaneously in their own memory, their own data. It's written here. Communication is done by calls to the communication primitives or library of Mpi. And the general object which contains this is a communicator, which is a collection of these Mpi tasks, which is called a communicator. Contains all the tasks which are able to communicate with each other, and the important parameters of the communicator is the size, which is its number of tasks, and the rank of every task. So it must be a unit identification number for every task, which is usually, in this case, is the number running from 0 to the number of tasks minus 1. This is the general setup. You have a communicator, and within this communicator you have a number of tasks, and every task has its own task ID. And in Mpi you can have different communicators, and every task will belong to one or more communicator. Another thing which we are using is a special case of MI programming. It consists in the way that every process is running the same program. So, SPMD, single program, multiple data. And the instructions and data are chosen from this program according and guided by the unique process identification number, by the task ID. So every task will can choose different instructions from the common program. So this is no loss of generality. That the programs are of SPMD type, because every task can do different things according to its own task ID. We have a single program, and every process will execute this program, but in its own context, and it's using its own task ID. So, Mpi is not only about sending and receiving, but it has components and functions for environmental management, basic point-to-point communication, of course, but also collective communication, and it allows to define derived data types, manipulate communicators, and a lot of things. Well, in this course, we will just restrict myself to the first four items. See, these have been already defined in the first version of MPI, and the later versions of MPI included different possibilities that showed up that they could be important. So, if you want to study this further over this course, the content of this course, and continue the MPI, you have the documentation, the standard documentation in the which are managed by the Mpi forum. And importantly, if you want to have short documentation, the man pages, you can, for example, use this of the Open Mpi organization. You have for every function of Mpi short description. There are some books which you can use to get explanations of in more details. Some of them are available on the web, others you have to buy. All this has been done, created the Mpi by the Mpi forum, which is a large community of users and manufacturers, and their website is this, and there you find all the documentation. Oh, as I said, Mpi only is a specification, and therefore we need also implementations. And the implementations translate the Mpi program machine-specific code and uses the underlying hardware of CPUs and communication system efficiently. So it's important that the implementation should be efficient to minimize the loss of efficiency application. You also have to have an interface for starting and controlling and stopping the processes. We have two implementations available at our clusters, which is Open Mpi and the Intel Mpi, which is provided by the Intel company. Just a short overview, what is good or not so good with message passing interface. Mpi is very good because it ties stability of all programs. You can run Mpi program on all parallel systems, desktop computer up to the largest supercomputer. If you have an implementation running on your system, you don't have to modify your program to run it on different kinds of hardware systems. And then the separation of specification and implementation is also very convenient, because you have a portability because of the standard, because this library is an established standard. And the implementation can be hardware specific and optimize performance. So the same program you can run efficiently on different hardware systems. And also you have a large number of routines in Mpi which simplify programming. Hardware routines which and communication patterns you could program yourself with send receive, but can be used with one call to one routine and simplifies programming, and it allows the implementer to do efficient implementation also for complicated communication patterns. So this is that's a good point for MPI. A bad point for MPI would be that MPI is MPI because it is message passing, so it requires distribution, exchange of data, which is cumbersome for setting up a program. But that it's necessary to use the large systems in any case, because they are they have distributed memory, and it's very, very large. The MPI is a library of very large number of routines, and so it's some difficult to know, to learn all the specifics, all the details of it. So you have to avoid to use too much of it, and to use it only if you really need some specific routine. So in this course, I will only cover a small subset of the abilities of MPI. Well, then MPI is, as I said, standard also specifies the bindings to Fortran and to C, but of course other programming languages have provided bindings. So I have given here a list, and for Python, I will give. I will use also in the examples. I will also use the Python programming language, and for this we have a implementation Mpi for Pi is available. Implementation for this you can find here on this places in the internet. Also, I have written an article for using Python, and in addition, we will have a section in this course especially for Python. Now, let's start with the basic ingredients for using MPI. There's the first, you have to use header files or modules where some basic definition of constants and data constructs are described. So you have in C, you have to include mpi.h, or in Fortran 77 you have to include mpi.f.h. Later version of Fortran you can also the use statement, use MPI or use MPI F08. So the header files are important. They contain the data types, the declaration of data types and some objects. And the most important object which will be used in every program is the object MPI world, and that's the communicator, which is the name of the communicator, which is created if you start your program. If you start your program with a number of processes, then automatically you will start, you will generate this communicator MPI world, which you will use later part of your program. There's an object in MPI or objects which are handles, and the handle is just a special object type. A handle is the name of the handle refers then to internal MPI data structures. So just MPI com world is just such a word, a handle to refer to the communicator. And all these objects, the handles you create or use will be available between the call to MPI init and the call to MPI finalize. Also, some handles are returned by MPI routines. The handle in your program is just the name of the stored in variables that are defined in Fortran as an integer, or as special types in Fortran 2008, or in C as special MPI types. We have a type MPI underscore com, the type the handle MPI com world in C. So then MPI specification has a certain layout. It is just called to a subroutine with some arguments. So you have a name for subroutine, and then you have arguments, and then the arguments are described with their intent, and the name is given here, and then what is the name, what the name stands for. So in this case, buff is the initial address of the receive buffer. Type is your choice, and then you have an parameter count, which is the number of elements, and the data type is the handle to the data type of each receive buffer element. Source is the rank number of the source. So on. So that's the description in the MPI standard is always in this type, where you have the calling sequence with the arguments and then the description of the arguments. And then the binding of this language independent specification is the following. There's naming conventions that have a reserved namespace, this MPI underscore. So this namespace must not be used otherwise in your program. Otherwise, as to call to MPI objects. And then all routines provide an error code. This error code is a return value in C, and in Fortran is a parameter. So you have one argument in every Fortran, or nearly every Fortran library call is the error parameter. Most MPI routines also use as a argument the communicator object. So in C, you typically have an integer arrow, and the arrow will be as return value of the call to the MPI function with parameters. And the rule is that for the C, the MPI is in capital letters, and the first letter of the name is also capital, the other is small letters. Fortran is a case insensitive. You can write it in or large cases, but you have to include also one additional parameter, which is the arrow parameter, which is an integer. Difference between C and Fortran for the and the syntax is given then in the description of the Mpi documentation. Fortran, you have this kind where the data types are here in this declaration. And in C, it's the same. You can include the data types just in the calling sequence of the syntax. Of Python, it's a different, because Python has particularities. You have two kinds of program for using the data. One with a small letter, the name. So if you have, for example, a receive operation, you will get the result you receive will be the output of the call, return value of the call. Then you, with a small r, you receive a Python object, which is just a collection of data which are defined, and which are, the definition is, so to speak, known to the name object. So you have to give just the source where the data come from, and a tag and a status. And in Python, because that's the binding to Python in this way is must include somehow the application of the data. Also has to include the structure of the object. So Python must be the implementation must somehow linearize this object. So if the object has a list or something, it has to be linearized in memory. It has copied to a continuous piece of memory, and then it can be transferred by send and receive operations. Then it has to delinearize to the object. It's time consuming to receive operation is time consuming, because the data must be linearized and delinearized before communicating them. So therefore, the MPI for Python also provides a communication routine with a capital first letter, which is used only for data which are already contiguous in memory. So say a NumPy array. So then you give just the address of the NumPy array, and this will avoid the internal manipulation of the object to a contiguous memory, because the data in the array are already contiguous in memory. And the error handling in Python is implicit. You don't have a error parameter. You use the exception model of Python to about the error. The outline of a program then would be the following. Fortran, it's just the include statement. You have to declare the integer error variable, and then you have to call Mpi init. Then you can invoke, after this call, you can invoke Mpi routines, and then you can finalize. You cannot call Mpi routines outside of this initialization and finalization. And for C, it's the same. You have a program main, and you have an init which also transfers the arguments, and then finalize. You don't have to have this error parameter. You don't have to use the error. And Python, of course, is still more simple. You just have to import MPI from MPI for Pi, and then invoke your the initialization and finalization is implicit in this import. Now, if you have compiled a program, then you have to start it. And for the starting, you have a command which is mpi run. And basically, you just say how many tasks should be started with the -n. Then you give your executable, which you have compiled with the MPI implementation. Python, of course, you don't have to compile, but you just have to run the program because it's a declarative language. So you have to give Python and give the script where your MPI Python program is written in. And there's also another MPI exec, which has the same functionality as MPI run. So now we come to the routines which manage the environment, which are MPI init, which I mentioned already, MPI finalize, and you can, within a program, if you have a subprogram or a subroutine, then you can inquire in the subroutine whether the main program already has initialized MPI. So there's a function MPI initialized, which gives you a true flag or a false flag. Then the most important MPI routines are the routines which inform about the communicator. You have one routine from size, which says you how many tasks in your communicator are available, and you have the rank, which says you what is the rank of the calling process in this communicator. And these are the most important information for your task to go to the common program. Then we have some additional interesting or useful management routines or information routines. You can get version and get the processor name, the name of the processor you are running on. And one thing is you can have a timing routine which gives you the clock number of seconds per system. And this you can use to inquire the performance of your program. And wtick says you how precise the resolution of your wtime implementation. So this is the most simple Fortran program would be just to call MPI init, call the size, and to call the rank of your task, and then finalize and then write your task ID. This is a simple hello world program for parallel message passing. So that's a program without message passing, but just a program for simultaneous execution on different tasks. And in C, it's the same. And Python is also the same. And here an example how the SPMD program style is very general. You can just if you have two tasks, for example, you can just say if task ID is equal to 0, then you call one subprogram, and if it's equal to 1, you call another one, and so you can do everything you want just with one program. In one program, you have all the different execution ways of all the tasks. So this is the introduction to MPI. Now see where are we in the time? About 12 o'clock. Okay, it's time for lunch break, I see. So I have used all the time for the general introduction and the principles. So we will start with the exercises after lunch break. We will now just stop. If you have questions, please ask them, and then we will have a lunch break, and I think we shall continue, let's say, I would like to have a bit more time at certain hours, later than indicated in the schedule. So if you have any questions, stop recording, okay. It's just also an answer to the question whether what front ends can be used. I think the new names for the front ends. Yeah, thank you. Recording. New ends, the names for the front ends, log in fast and so on, but the old names are valid again still, and I use GWDU 103, but you can also use the GWDU 102 or 101. And I think all the stuff with login and so have been dealt with yesterday, and you have successfully logged in. And then all the examples are written in 3 versions for Fortran, C, and Python. My own background is in Fortran, so I will explain everything in Fortran, and at some point I also have some examples which are only in Fortran, not in C or Python. In any case, Python will be covered in more detail in a later section of this course. Now, if you have copied everything, then we need to learn to compile and link and start programs on the front end. So if we want to execute our programs on the cluster, we have to use the Slurm system, and we have a number of nodes reserved for this course, which are available under the name reservation PCHPC, so Practical Course for HPC course. So we will see to use this reservation to be sure to get some hardware to run on. Okay, batch processing was dealt with yesterday also, so I don't have to go into this. Now let's start with the simple Hello Mpi program, which I give here in Fortran and C and Python again. And to find these programs in my directories Übung _ F or C or Python in the start directory. Now, as I said, We can use different implementations for MPI, which is one is Open MPI, the other is Intel MPI. Now, how to select one of those? They are selected by loading the appropriate modules. So let's start with Open MPI. You have to load the module for Open MPI with module load Open MPI. And I have also prepared in the parent directory a script which is called modules_mpi.x, which you can source by writing dot, then blank, dot slash modules_open MPI. Then this will be executed and you will load the MPI, Open MPI environment. And particularly in this environment, the compiler for Open MPI are available, and the compilers have the name Mpi Fort for the Fortran program and Mpi CC for a C program. So if you want to compile and to link the program hello MPI, you have to write this Mpi Fort -o hello. So this is the name of the executable which will be produced, and there's the name of the program, hello_mpi.f. Same with C. And there's also a make file which you can use. Now you can also, instead of OpenMPI, you can use the implementation from Intel, and you have to load different two modules, the Intel 1 API compilers and the Intel 1 API MPI. And again, you can load these modules explicitly or just source the script file in the parent directory modules_intel.x. And then the names of the corresponding compiler in this implementation have the names Mpi iFort and Mpi ICC, so an additional I. You can compile and link and produce the executable with these commands, or use the makefile, but you have to look into the makefile which compiler is activated. In this case, you have to write the Mpi iFort or Mpi ICC compiler in the makefile. We have to modify the makefile probably. And finally, for Python, you don't have to compile, just can run them, but also you have to load the corresponding module to have the MPI for Pi environment available. So you have to load the modules OpenMPI and Python in order to execute in the program. Okay, then finally, if the compilation and link step has been done, we can run the program, for example, with Mpi -n4 and then the executable. In Python, you just have to call the Python with the Python file. Okay, this is the way to start the program, and then it's running on the front end. Front end, of course, you can run parallel programs because the front end has several cores, and so you can also use the parallel program on the front ends. But eventually, you would like to use the cluster resources. And for this, you have to start to access the cluster with the slurm commands. So there are two possibilities. You can use interactively the cluster resources by allocating with salloc. For example, with salloc minus p medium minus reservation with our course, you can require 2 cores and 2 tasks per node, two nodes and 2 tasks per node. You can write out this command, or you can source this command file, which I provide with salloc command. And then you will see that you get allocation, which gives you the name of the nodes. You will find different nodes in your example. This is for a former reservation. But if you ask for the, you get a shell. If you ask for the host name, you will see the shell is still on the front end. But if you then do the MPI run, you will see with the hello, you will see that the program is running on the nodes of the cluster which have been allocated with salloc. So that's a possibility to start interactively jobs on the cluster with salloc. And then you can start the MPI job in batch mode with sbatch. And again, you have to give the location of the nodes which you want to access with a partition. And yeah, I omitted the reservation, but you can use also the reservation. And then minus wrap the command. This is just one command in the batch in the shell, but you can put this command also in a batch in a job file, which has this structure where all these arguments are given with the cross sbatch prefetch preface. So sbatch, this is the time and the number of nodes you want and the number of tasks per node and so on. And then the program will be started with MPI run, and you don't have to put here the number of tasks you want to produce. They are just the tasks will start on all nodes, on all end tasks on nodes which have been indicated here, required for use. And then you will get an output if you start this job script with sbatch job script. You will get an output which is written in a file in the directory where you started this sbatch in the file storm with a number for, with the job ID number .out. Okay, these slurm commands, I will repeat them, which you will need frequently here, which is if small n, just give small n, you can require a number of nodes, of cores, which will be distributed by the system onto nodes which are free. Or you can give with a large n the number of nodes you want to use. You can give just one number which gives you the minimum number of nodes, or you can also put a minimum and a maximum number. And then you can give the tasks per node, which then will start the task on this number of cores on each node. Then you can also modify the name of the output file. And then you can use information about the slurm system with sinfo, shows all the partitions available and their status. If you want to inquire to your batch job, you just say sq minus your username. Or you can get information about the status of your job running job with as control show job and job ID, and you can cancel a job. That's also important. If you see it's hanging or something, you can cancel with S cancel the job ID. These are the most important Slurm commands we will be using. Okay, so far for the information about compiling and linking and executing. And this information you should now try to put into reality on your own login shell. So just do this exercise 1, connect, you copy the directories and load the model files, compile the program and run the program, and try to do it locally and on the cluster with salloc and with sbatch, and try different numbers of nodes. So I think this you should do in the breakout rooms or in your own login shell, and I give you some time and say 10 minutes, and then we will meet again and in the broadcast. And if there are any questions, of course, I will try to answer them, and or the people in the breakout rooms will work together to find solutions. Okay, I will continue at 13, say 22. With the exercise, with the next exercise. And I think I will stop the recording. Thank you. Message passing, the basic mechanism for message passing programming. I have to transfer messages or data into steps. One step is sending into a system buffer, and if I want to use the message in the destination process, I have to receive this data from the system buffer. So that's the two-step way to do message passing, sending and receiving. Well, in MPI, we have our communication, our communicator, Mpi com world, and in this we have several processes or tasks from, in this case, 4, and then between 2 of the processes I will exchange messages. So I have from one process to send, and another process has to receive, and the message will be composed of data and by some envelope which contains the destination and the source, and additionally if you want a tag to identify the message. Of course, it's also possible to send a message to the process itself. That will also be possible. So the destination and source could be identically. Now, what is a message in the MPI context? Message contains a number of elements of the same data type. So it's, it's a tuple of same data types, an array of same data types, elements of the same data type. And the data types can be either the basic data types of the underlying programming language, which are, of course, can be different in Fortran and C. And MPI also allows to declare, to construct derived data types, which can be built from the basic or from recursively from other derived data types. And then to indicate which data type you are using, you have handles, which are the names for the data types, and are the behind the names, then there are the data construct which describes the outline of the data type, the layout in memory. So we have data types, and of course, because C and Fortran have different data types, there are different names in MPI. So the MPI data type is called MPI integer if you want to use a Fortran data type integer, and MPI real, MPI double precision for double precision, and so on. And again, for C, you have the name MPI int, long, float, and so on for the C data types, which are indicated here. The most important, of course, are MPI int and MPI float or MPI double. And still in Python, you will have the name of the data structures of the handles is MPI.int and not MPI_int. So the message, the message is written in a message envelope, which contains the additional information in which communicator context the message is passed, and this source and destination process must belong to this communicator, and then it contains the rank, its source and destination in this communicator, and additional an identifier which can be used to differentiate between messages. And this tag can be specified by the user as an integer, and the range of the integer which can be used is between 0 and an upper bound UB, and the value of this upper bound is implementation dependent, and you can see the value with the MPI constant, which is written in the header, MPI_tag_UB. And the standard requires UB to be at least 32,767, but usually it is much larger in the most implementations. But in any case, you can so many different tags for different messages. Now, the syntax for the operations, for the send operation in C is you have to give, let me see. Okay. You have to give as parameters the starting address where the message, where the elements are residing, the number of elements and the data type of the elements. And you have to give the destination, the rank of the destination, and the number of the value of the tag, and the communicator. Fortran's the same, where you have the same elements, and you have in addition the error parameter and the count, data type, destination, tag, and common AR are all integer numbers. And in Python, again, you have two versions, two variants. With a small first letter, you can send objects, and with a large S, you can send regularly data structures as a, for example, an Mpi array. So this is a operation to send a message, and the corresponding receive operation has the same arguments. You give the starting address where the data should be written in memory, the number of elements of a certain data type, source from where the message should come and the tag. And one additional parameter is here the status. We come to the status in a moment, but this is just the information what the message contained. It's, properties of the message which were exchanged. In Fortran, and this status is important because you don't know beforehand what in your internal buffer, what kind of message has arrived in your internal buffer. So you can inquire the properties of this message, so the origin and the tag and the size of this message by the Mpi status parameter. Mpi status data structure. So in Fortran it's the same. You have a status in addition to the usual arguments. Also in the sending process you have a status argument, and the status is an array of a certain number of elements, which size is Mpi status size. What is contained? Oh, in Python, you have the two versions with the small and the large first character for Python objects or for arrays, NumPy arrays. And you see, in one case it's a return value, in the other case is the address of the memory location where the buffer will be will be stored. And here you can write the status. The default value is status none, so that you don't want to retrieve the status. Now there's a very important restriction for a valid data exchange via message passing. That is that the size of data to be received. So the size, the size of the data to be received is the count times the size of the data type. So this amount must be larger than the size of the message which has been sent and which is pending. So receive count times the size of the data type received must be equal or greater than the send count. Otherwise, the program will be stopped with an error. If you don't can use wildcards. Why? The receive copies a pending message into the place it prescribes in its parameters if the source and the tag attributes of the message envelope conform with the source and tag arguments in the call to Mpi receive. So now if you don't know or don't want to differentiate between the sender or the tag, you can use wildcards. So for receiving by giving Mpi any source, Mpi any tag. That means that you just receive the message which is pending, independently whether what source, from which source it came, or which tag it had. Now the status argument can be used to retrieve the actual size and the actual values of source and tag from the message. If you don't need this information, you can use as an argument, instead of a status variable, you can argument Mpi status ignore, or omit the status argument at all for Python. So if you don't want to know and to use this information, you can just write Mpi status ignore as an argument. Now, what can we retrieve from the status? The type of the status argument is Mpi status in C, and an integer array of size Mpi status size in Fortran, and just an object of type Mpi status in Python. Then you have the following information: the element stat.mpi source. If you have an object stat, the element Mpi source gives you the source ID. And in Fortran, it's the element Mpi source of the array status. And again, in Mpi for Python, it's the stat.get source. Then you can, in the same way, you get the information about the tag of the message with the element Mpi tag of this data structure, or the element Mpi tag of the array. And then you can also get, again, the error from the operation, which is redundant because you get the error also as a return argument. And then important, you get the count, the number of elements which have been transmitted into the by the send operation, and which you want to receive now. Now it's important to realize that the message for the system just says a given size in bytes, and the system doesn't know which data type it's the message contains. The system only knows the size of the message. So if you want to have a count of the number of specific elements, you must know the data type of the message. So you can get the count by calling a function Mpi get count, and as argument you give the address of the status argument, and then you give the data type which are transmitted, and then the system, this function calculates the number of counts from the amount of from the size of the message, and divided by the data type. Same in Fortran, you have to call a function Mpi get count, and as argument you give the status variable and the data type, and then you return, you get the number of elements which are given in this message. And in Mpi for Python, you just take the element of the stat data structure get elements of data type. And you also can directly get the size in bytes, but only in Python, which with stat get size. So the most important thing are here the source and the tag and the number of elements received. Now, we saw that restriction which says that the receive count must be large enough such that the amount to be received must be larger than the size of received values must be larger than the size of the message which has been sent, because otherwise you will not have enough place to store the message. In order to prevent a stop of the program because there is too less place for storing the message, you can probe the message before actually receiving it. So the status argument can be inquired before actually receiving the message. So with the function Mpi probe from a source and from a source with a tag, and you give the status argument, then you can inquire from the status argument all the properties we have indicated here before actually receiving the message. So then you can look how many elements the message contains, and then you can accordingly program the receive operation with the needed number of elements to receive. So you can adjust the count of the elements to be received to the size of the message. This is one point. The other point is you can select messages from particular sources if you want, or with particular tags which you want to receive or not to receive. So that's a way to use the probing message before actually receiving it. Okay. Now we have to look about up now we have discussed the syntax of the send and receive calls, which arguments you have to put and what is the meaning of the arguments. Now we have to discuss the semantic. What does the program do? And in which way the program is running and accomplishing its message exchange. So an important point is that the calls to send and receive are blocking. That means you can proceed with the program only if the Mpi send or the Mpi receive have been completed. So the completion of the program is different for sending and receiving. And for sending, it completes if the message data from the send buffer are copied to another place. And the important point is it completes if the send buffer can be safely reused, so that the data which have to be sent are really in a different position. so you can modify the original data, the original memory place. So, and now it means that the sending is local. It means it depends only on the process which calls the send if the message data are copied to a temporary buffer. And then the program can proceed in the sending process after this copy, after the data are copied in a different place. And this can be before some receive process has really received the data. But it's not non-local if the message data are not copied to a buffer, but are copied directly to the receive, to the memory of the receiving process. Then it can complete only when the receive call has been posted and the received and all data have been received in the destination process. So it depends how the message is handled by the system, whether it's copied temporarily buffered or not. So the send operation can be local, can be performed local or ending locally if the message is intermediate is copied, but it's non-local if it's stored directly in the receive memory, in the receiving memory. And it depends on the program procedure in the receiving process. So, and the choice whether the sending is buffered or direct is implementation dependent. We'll discuss this in a moment. Now, the receive operation itself is always non-local because it's only completed if data have been, of all the data from the message passing has been arrived at the receiving process and are stored in the receiving memory. So that's the semantic. Now the choice between buffered and direct sending can also be steered directly by the user because there are explicit modi for the blocking send. So MPI provides a special routine for a buffered send where the user can define a temporary buffer and attach this buffer before sending of a large enough size. And then if it uses bsend, then the data will be buffered in this attached buffer, and the send call will return, and you can continue your program in the sending process. And of course, this is has low latency because the sending process will continue very fast, but it has a low bandwidth because the data have to be copied intermediately, additionally to to a temporary buffer before being transferred to the receiving memory. Then we have a synchronous send with a S send, which is always non-local because then the data are not buffered temporarily, but they are directly sent to the receiving memory. And so the sending process only can be completed if all the data have been sent and received in the receiving process. This has a higher latency because it has to establish the communication channel before copying the data. But if the channel has been established, it can transfer the data without additional copying. So it has a higher bandwidth. And then there's a ready send, which is somehow a very special kind of message passing. It assumes that the receiving process has already posted its receive call, so that the receiving process is ready to access to receive the data, and so can directly receive the data from the sending process. So it's non-local. So, and in any case, it will fail unless the matching receive has been called before the send process has been started. So it's a very unsecure kind of communication, because normally you don't know at what time receiving call has been posted in a different process. So you shouldn't use this. So usually you can choose between B send and S send, and the normal send without an additional letter here is just a choice, one of these, where the for the buffered send, the temporary buffer must not be allocated from the user, but will be provided by the system. But the system decides how large this buffer can be. So the standard send will switch from buffered send to synchronous send if the message size exceeds a certain threshold. So you don't know when the send process will be switched from a local to a non-local blocking, from a local to a non-local blocking mechanism. So here I just indicated again how to call to use the bsend operation. By calling, you have to touch the buffer of a certain size, and then after sending you can detach this buffer. And the size of this buffer you have to give in bytes. So, and the size must be large enough to contain the number of bytes in the send buffer, so the count times the size of the data type, plus you have to give some additional bytes in this side, some additional size for the buffer, which you don't have to know yourself, but you can give this constant, which is in the system Mpi bsend overhead. It's predefined and given in given by the system. Okay. Now to picture the program procedure for the different kinds of send body, you have here a picture for a synchronous send. At some point, the sending process puts a send call, and this will trigger a message, sending the message envelope to the receiving process, where somewhere in the system this envelope will be stored. And suppose the receiving process has posted a receive call should, even before the send call has been posted in the sending process, then the receive call will inquire in the system whether some message has arrived, and it will wait there until a message envelope has come. Then, if the message envelope has arrived, then it will notify the sender that the receive process is ready to receive data, and then the send process will start to send the data and will send all data. And after the last byte has arrived, the receive call completes and the program can go on. And here, after the last byte has been sent, the send call completes and the program can proceed. Now in the buffered send, then the send call will copy the buffer in some temporary buffer, and at the same time will send a message envelope to the system buffer, to the system of the receiving process, and again then the receive call will inquire whether some messages has sent an envelope, and if yes, it will notify. In this case, it will notify the temporary buffer to send the data. But the send call itself can complete before, just after the data have been copied to the temporary buffer. So send has not to wait until the data have arrived in the receive process. And again, the ready send is only it's only valid if the receive has already been posted, so that the envelope will reach a ready receive buffer, receive call, and so that the data can be streamed directly to the receive memory. Then is one further point. What happens if you have multiple messages on the same connection, so with the same source, same source and the same destination? So if several receive match several messages, the sending order is preserved. So messages do not overtake each other. Example, if you send two different messages from the sending process, and in the receiving process you say for the tag MPI any tag, then you are sure that the first message sent will be received as the first message in the receive process. But of course, if you explicitly state which tag should be received, then of course the messages might change the order, because if you want to receive at first the message with tag 2, then you will receive it first, even if it was sent in the second place. Finally, you often have the situation that you want to send to exchange messages. You send something to a neighboring process and you receive something from another process. So you have to send something to process 1 and to receive from process 0 to receive something from process 1, and conversely from process 1 you send something to 0 and receive something from 0. Now If this is done with buffered send, then it looks like following. You send something, buffered send, you put your data in a intermediate buffer, and then you return from the send call and can just execute the receive call. And that you can do because the buffered send is a local operation. You don't need to know what the other process has been done because the data are already stored in an intermediate buffer. So in this case, both processes just can do their sending the data into some temporary buffers and then receive the corresponding data from the buffers. But what is if you use synchronous send, you're stuck because the synchronous send can only complete if a receive has been posted and can receive the data you have been sending, but the other process is also sending, and so it waits for a receive from the first process. So you will never get a match, and you have a deadlock. So in this case, method exchange with synchronous send is never done. What you could do to break this deadlock is just to reverse the order of receive and send on the process. So process 0 sends, puts a send call, and the process 1 puts a receive call in the first place. And then the send call. Then you have the sending in the first place and the receiving in the second place. Oh, because this situation occurs quite frequently, you have a special MPI routine for send receive, where you put all this information for sending and receiving into the same into one call, send receive, and then you will send some data to the EPN and you receive some data from EPN, and this replaces the two calls to send and receive, and you don't have to worry about the order because the system guarantees that no deadlock will occur. And of course, the neighbor depends on the process you are. If you are process 0, then the neighbor is 1, and if you are process 1, then the neighbor is process 0. Okay. So far for the semantic and syntax of the and the properties of the point-to-point communication, of the blocking point-to-point communication. Are there any questions so far? Okay. Then I will proceed to the non-blocking communication. So we had discussed the blocking, which was a routine return only after completion of the intended data movement. Now the non-blocking communication calls, in this case, the routines, the calls to send or receive return immediately, so the program can proceed without knowing whether the communication has been completed or not. And therefore, the completion of the communication must be monitored explicitly by special MPI routines for testing and waiting for the completion. And the user is responsible to use data from the send or receive call only after the completion of the communication has been indicated. So that's the user responsibility. So you could program something where you use data which have not yet been sent. Would be fatal. So why do we need or want to have non-blocking communication? You can overlap at the same time, do communication and working with data which are not involved in the communication. So if the communication is performed by some additional hardware, communication hardware, then you can use the usual hardware to do other communications in your program. And you don't have deadlocks because the programs, the calls return immediately after posting them, and you avoid temporary buffering of messages with buffered send. So now how is this affected the non-blocking communication? You have two steps. You have to post the call, send or receive, and this is done with the name which starts with an I. So Mpi I send is a non-blocking send, or Mpi I receive is a non-blocking receive. Then you can do anything you want, and if you want to use the communicated data, you have to ensure that the communication has completed, that you can do with a waiting or a testing call. You can call to an Mpi wait for the completion of the communication, then your program will only continue if the communication has, at this point, if the communication has been completed. Or you can put an Mpi test, where the program which tells you whether the communication has been succeeded, and you can decide on the ongoing computations according to the result of the test. And this is both for sending and receiving. You can use sending. You can use non-blocking sends with blocking receives, or non-blocking or blocking sends with non-blocking receives together. So the way to test for communication, in order to test this, you have to somehow to refer to this communication, and this is done in terms of a request object. So if you call a non-blocking communication routine, you will, as an argument, get a request handle from this call, which is one of the arguments in the calling sequence. You get a request handle, and this request handle then can be used to be put into the wait function to test, to wait or to test for this particular communication with this request handle, the respective request handle. So as I said, you can use non-blocking communication with blocking communication calls, or you can also use non-blocking send and non-blocking receive. So you can mix them freely. So the syntax is as the usual communication, but in addition you have as an argument the request data, the request object. Now this is a special data type for C of type Mpi request, some name, and for Fortran it is just an integer. And in Mpi, it's a return value for the call to the I send with a big I. So for sending NumPy arrays. And the receive is the same. You just have the usual arguments of the receive call. But in addition, you have this argument of the request for this receiving communication call. And you will see in the I receive argument list is no status argument, because if you call this, you don't know. If you call and receive, you don't know whether their corresponding send has been posted. So you don't know. You cannot. You cannot have information about the message at this point. You can have the information only if the communication has completed. Therefore, the status argument will only be can only be used in the wait function. This here, the wait currently has as an argument the request handle and then the MPI status. And then you can inquire the properties of the message from the status argument. And wait is, as I said, is blocking until the operation has completed. And if the request was created by receive, the status contains the corresponding information. If the request was created by a send, then status is not defined. So there's no point to inquire the status of the sending message, because the sender, of course, knows what he has sent. So as a picture, in the program, the timing of the program, you have advancement of the program. You put the I send, which then will send a message envelope to the system of the receiving process, and then it returns immediately. You can do other work, and there the message envelope stays until a receiving call has been posted for the receive processor, which inquires and sees that the message is there, and then there is a notification. Then the data will be fetched from the memory of the sending process and transferred to the receiving process. And at some point, the the sending process will post a wait, and then this wait will inquire whether the data have been transferred or not, and the wait will be notified if the data has left the sending process, and can then proceed in the program. And the same is for the I receive. You put the I receive and can do other work, and then you have to wait until the notification comes that the data have all sent, have been sent by the sending process by the send operation. Of course, here you could also do the same picture for corresponding picture for communication with I send and I receive. And again, this is a picture for a message exchange when both processes do an I send and a receive. And of course, because the I sends return immediately, the receives are posted and can receive the data. And accordingly, after the wait, the time, then the program will proceed, and you will not get into a deadlock. instead of waiting, you also can testing the proceeding of the communication, where the MPI test function will give you a flag which is true or false, if corresponding to the operation being completed or not. And then you can decide whether you reuse the memory space from where the data come or where the data have been stored. Okay. I see this has covered all the properties of the point-to-point communication, and see we are due for a break, I think. Overdue to a break. So I think we make a 10-minute break until 15:15, and then we will proceed to the exercises for point-to-point. So but if you have any questions, you can just ask, and I will try to answer them between. We'll stop. So the first exercise would be just to see a send receive at work. So you have two processes. Example is two processes. In each process you have an array of 10 elements, and you want to transmit the sum of the elements of the array in process 1 to some place in the array process 0. So you have in Fortran you have a double precision array of VEC size 10 elements, and you want to send 3 elements and you want to receive 3 elements, and you want to receive the elements in process 0 from any source with any tag, and you store these elements and receive 3 elements starting from the address VEC of 2, so starting from the second element here. And in the sending process is process 1, you want to send the number of elements and send starting from the place 5 in this array. So the address would be VEC of 5. So this is a short program which is in the directory /mpi-p.p, p2p. And there you have the program p2p vector.f, and you just should compile and run this program on 2 processes and see the result. And you see which is important. You have to look that the data types confirm on the sending and on the receiving process. You must have a declaration that the vector has a data type double precision, and therefore you have to send double precision data and to receive double precision data. It's and for Python, you have that the information about the data to be sent on and to be received are already in the you can put this information into the argument, the vector of starting from start send up to start send plus end send, and receiving at start receive. So you don't have to have all these arguments of buffer and sending number of sending types and so on. And then you just should run this program and then try to modify the number of received elements or the number of sent elements to smaller, larger ones, and then you see what happens. Okay, there's this question, the advantage of sending data type in. Of course, you could also use the data type Mpi byte, but then you have to always calculate how many bytes do you need to transfer a certain number of integer or double precision elements. So it's simpler to use the cost spending. Okay, I think Jonathan Decker has a similar argument here. Okay, just try this and see what happens. And as an answer for Eliane, is you would have, if you use the data type Mpi byte, you cannot use size of type for count, but you would have to use count times size of byte count, because the total amount of bytes would be the size of bytes of the type times the number of elements you want to send. And the answer to Pia is we have already continued. by the status argument. So the status argument, I repeat here this slide. You can get from the status argument the source from where the message came, and you can recover the tag, retrieve the tag, and you can get the number of elements which have been of a certain data type, which have been transmitted in the message and which you can receive. Now I have prepared programs, P2P status, where I have included the call to get counts. And you should modify it and complete the code to retrieve also the source and the tag of the received message and print this out. You get a feel what you can do with the status argument. The important point, one point is already included in the program which is provided, but you should complete it further by retrieving the source and the tag of the message which had been sent and which shall be received. Okay, this is, I think, was easy, but now we want to use the status argument to probe the message. So in the first exercise, that it's dangerous if the size of the receive buffer is too small. So if you don't know beforehand how large the send buffer is, then your program could fail if you provide a too small receive buffer. So you can think of probing the message before you receive it with using the Mpi probe. The Mpi probe has as an argument the status, and then if you call Mpi probe, you can inquire the status argument for the size of the message. Mpi get count. And then you can adjust the receive buffer according to the count of the message to be received, which has been sent. So just in the program determines the N receive buffer according to the probe. You have to call the Mpi probe, and then you can inquire the count of the status argument, and then set accordingly the receive number of the number of element to receive. Okay, we want to continue. Another problem. And this is also a thing which appears often in applications, that you want to shift clockwise data around a ring of processors. So in this case, example here is you have three processes, 0, 0, 1, and 2, and you send something from 0 to 1, and from 1 to 2, and from 2 to 0. So 0 sends something to 1 and receives something from 2, and so on. So every process sends a vector with a certain number of elements, NL, to its right neighbor, and receives something from its left neighbor. So I have a program which is called deadlock, and I want to show what happens if the size of the data you want to send and receive becomes larger and larger. What happens? So I will just do this in my login window. So I compile it. I just load the Open Mpi environment, implementation Open Mpi. Then I compile Mpi fort program p2p deadlock.f. And let's have a look into this program. Or so what do we have here? We have a loop over the length of the vector, which goes from 10 to the loop. So from 10 to 10 to the 8. So it becomes very long. A large amount of data to be sent over the ring. And I just put all elements of the vector equal to my ID. And then I write out my ID, the length, and the first element. Before sending, I write what I have in my vector to be sent, and then I write down what I have received. So this Mpi I run, say, on 3 processes. I've compiled it for executable, which is called a.out. So what happens? Start value on process 0 is 0, on process 1 is 1, on process 2 is 2, for the length 10. Then after the ring shift, I get on process 1, I get the value of 0 because I received it from process 0. And again, it gets larger. I always send something, I receive something, but if the size becomes 10,000, I just get the start value, but I don't receive anything anymore. And what's the reason for this? As I discussed, the send modus is implementation dependent. So if the size of the message exceeds some some value, then the modus changes from buffered send to synchronous send. And for the synchronous send, we have in the program, if all processes do at first a send and then a receive. So if I have a synchronous send, then all are sending and they don't come to the point of receiving. So I have a typical deadlock. And the deadlock occurs if the size of the data are larger than 1,000 times the size of a double position. So I have to stop this. Oh, I want to do the same thing with the other implementation, the Intel implementation. So now I load the modules for the Intel implementation. Then I compile the Intel compiler, Mpi iFort. That's the Intel Mpi compiler. Then I run it again. You see, the Intel compiler proceeds to a much larger value of data. And even for the largest value of data, it uses the buffered send mode. So the implementation dependent border of between buffered and synchronous send is different for these two implementations. But if you develop some program and you don't know, you cannot be sure at which point the switch between buffered and synchronous send occurs in the implementation where your program will be used. It's more safe to avoid this kind of programming where it could occur. So the best thing to test this very fast would be just to enforce in the program a synchronous send. So let us see. this program, just modify it by using a synchronous send instead of a normal send, which chooses buffered send or synchronous send according to the implementation. But now we enforce the synchronous send from the beginning. Compile it and now run. You see, even for the smallest value of the message, the smallest size of the message, the program blocks because always the synchronous send is used. Okay. Let's return to the exercises, the other exercises. Now I have shown you what the exercise 4 was meant to show, that it might be easy to produce a deadlock. You have to worry about it in your programming, that you don't come to this point to use a deadlock inadvertently. Oh, now you can play with the program how to avoid deadlock. There are several possibilities. First solution would be to change the order in one process between receive and send. So, for example, for process 0, you post the receive before the send. Then, of course, the deadlock is broken. Another solution would be to use buffered send explicitly by providing a user-defined buffer with buffer attach. Then use the buffer send. So this would be here the syntax for Fortran, syntax for C, and syntax for Python. Finally, it would be possible to use the send receive, which combines sending receiving, or you could use the non-blocking send. So in Fortran, you define a variable integer rec for where the request handle will be stored, and then you call the MPI isend every process, which returns a request handle, and then you make a normal receive, blocking a receive, and after the receive you call the wait function, and that it is. And this guarantees that the isend returns immediately, so that the receive operation can be called on any process. Okay, this is just the programming for Fortran, for C. Fortran was Fortran. This was C. We have the type is Mpi request for the request variable. And for Python, again, it's the request handle is returned the isend function. Okay. So now I give you, say, 5 minutes to test one of these solutions and to verify they really don't lead to a deadlock also with the OpenMPI. So I continue. Just to see what happens with the different solutions to break the deadlock. I change the order in process 0, receive, send, and I will at the same time every process will put a send, only the first process will put a receive, and so it can receive the data from its neighbor, process 1. And then process 1 is ready to complete the send operation and put the receive. So after this, then can receive the data from process 2. And process 2 then again is ready to put the receive after the send, and so it can receive the data from process 3, and then only the process C can put its receive call to receive the data from process 0. So somehow the receive the cycle ring exchange cycle is serialized because one pair of processes after another can do the receive in this way. So that's what be a solution which is not very efficient, not very because it's linear in the number of processors. Now, a different way to do it would be with the ISend. Then every process puts an ISend, and immediately after it can put it receives. So the communication can start just after the sending. Then only they have to wait until the communication is completed. So it's a simultaneous communication due to the non-blocking receive operation, non-blocking send operation. Okay, that's the difference. Okay, then we could use the functions we have now at our disposal, the sending and receiving, to streamline our prime program, so that the output from the testing can be a bit more collected, so that only one process will collect the divisors found. So you could define in the prime program, which we had last section exercises, define an array with number divisors, numdiv, of size of number of processes. Then every process can send its detected number of divisors, one number, to the, say, to the zeros process. The zeros process does a loop and receives from every process this number and stores this in the array with argument of the number of the sending process from where it receives the data IP. Then the process 0 prints just the number one after the other. That would be a better display of the result. This you can do as your homework. But let me ask one question we can discuss here. What would happen if we use, instead of standard MPI send, the MPI synchronous send? Just looking at this code, what would happen? Can you answer this? Some of you can answer this. I put here an send instead of send in every process, and then a normal receive. That would be an answer, not all ND arrive. Why not? Imagine in processor 0, the processor 0 will send, a synchronous send, and then in this loop it will put a receive from itself, from IP equal to 0. I think this answer of Jakob is not the essence. They are not dropped, but they are hanging. The sends are hanging if no corresponding receive is posted. So they can complete only if a corresponding receive has received the message. And of course, if I have an send on process 0, on process 1, for example, then the process 0 will sometime call the receive from this process 1. So it's okay. But on process 0, which also calls this synchronous send, then I also have here for IP equals 0, I process process 0 calls receive from process 0. So it would wait to, the receive on process 0 will only can only be matched if the send on process 0 has finished and is a synchronous send. And the synchronous send will not complete until the receive has been posted. So this is a typical deadlock situation. Because you have, in this case, one on process 0, you have a send from process 0 to process 0 that never can be healthy in with a synchronous send. And send does not have this problem because send switches between buffered send and synchronous send, and for such a small message, always buffered send is used. So there's no problem with buffered with a normal send in this case. Okay. Finally, oh yeah, it's one remark. I have completed solution for the most of the programs in this directories, so you can look up if you want to have the completed solution in these directories. Now, as a last point, I would like to demonstrate the speed of communication just with a ping pong program. Ping pong program means that I write a message to an yeah, there's a question. To download all those files, that's just you copy them just in your directory from my directory. In the presentation this morning, in the first exercise section, I have given the, oh yeah, I see there's an example, but you should complete this by a /* because copy Übung _C /* so you get all files and then a dot. So if you have it in the folder on your machine, you can copy it to your local machine in the second step. Okay, there's another. Now I come back to the ping pong. See the speed of communication. This program just sends from process 0 to another process amount of data with larger and larger data size and reports the time and determines from this the latency and the bandwidth. So just want to demonstrate this. I have the program P2P. Just go mpi.f and I just see module, what kind of implementation I'm using are the Intel. So I have to MPI for program, then MP run minus N4. So with now if I use 4 processes, then I do the ping pong consecutively from process 0 to process 1 to process 2 to process 3. So I have 3 communication parameters between these 3 communications from 0 to 1, 2, or 3. And the result will be here. From process 0 to process 1, I have a latency of 0.31 microseconds and a bandwidth of 9 gigabytes. So times this 64 gigabit. And to the process 2 and 3, I have a larger latency in the smaller bandwidths. And that is due to the hardware architecture of a node, where some 2 cores are on the same die, I think, and so they have very fast communication into the other cores. The communication takes more time, so it's slower. So you can, but these are the order of magnitude, and you can start the same program on the cluster and between different nodes, and you will also see the difference between latency within a node, bandwidth within a node, and between nodes. That you can check out yourself. Okay. This is the end of the exercises for point-to-point communication. And the next point I will discuss is the first full application, parallelizing the full application of a numerical integration for determine the value of pi. And before starting, I will make a 10-minute break, so we will meet again at 16:25. The approximate calculation of pi by numerical integration. Of course, the number pi is just 4 times the area of a quarter circle. So you have the integral from 0 to 1 of the square of 1 minus x squared times the x. So this example, all my examples are somewhat physical or mathematical oriented, because that's my background, and I hope it's simple enough mathematics that you can follow it. Okay, if you do this integral by numerical integration, usually you have an integral from lower to high boundary function dx, and divide the integral into strips of some width, and you divide this integral as a sum of integrals over all the strips. So it's a sum over I strips where you have the integral, and then you approximate the integral in a strip just by taking the mean value of the function values at the boundary. So you approximate it by the width of the boundary times the value of the function in the middle of the boundary of the strip. So the approximation, the total integral is the approximation plus a remainder, and the approximation is just the sum of all function values in the middle of the strips times the width of the strips. We have the sum of n function values times the width of the strips. Okay. The function in our case is square root of 1 minus x squared. So we have to implement this simple numerical integration in the program Mpi for Mpi approximation. You have to read the value of strips, of the number of strips you want to use. Then you sum over the n strips and write the result. Fortran implementation for the calculation would just be if you have given the number of strips, you have the width of the strips is 1 because the total integration domain is 1 over n. And then you take the middle value of the strip, which is I minus 0.5 times the width of the strip. And then you add all these values, the function values at this point, xi square root 1 minus xi square, and then you multiply it by 4 and the width of the strips times this approximation. This is the approximation for pi you calculate. Very simple. Let's do this in this program, which is in the folder Pi. There I have the Pi approximation program, which I file Mpi I think I have. Okay, I have to share my terminal with you. I thought and I do it on because it's a sequential program on one process. So I'm asked to choose a number of strips, say 100,000. And you see I get a number estimated number and the error is this. So that's very easy. But now I want, of course, to parallelize this application in a way that I want to distribute the calculation of the function values in the strips on the different processes. So if I have 4 processes, then I just calculate this strip, the function values, blue one on processor 0, the green one on processor 1, and so on. The round robin distribution of the strips across the processes. So this is exercise for you to do or to contemplate. How is this done? Stepping from the sequential program to a parallel program. See what you have to do. I have listed here all the steps. Set up the MPI environment, so you have to call for the number of processes and also the size of the communicator, and you have to establish your own rank. This calls to MPI com size and MPI com rank. Then for one process, say the process me equal to 0 for the task ID 0, you read the value of n from standard input. Then you have to distribute this value to all tasks. Then you collect on each process the strip, the values for the function values from strip 1 plus me and sum every np's strip on task me. Then you get np local sums for the strips you you calculated in your process, and then you have to add all these local sums on one process, say on process 0, to a total sum. So you get the total sum on process 0, and on process 0 then you can write the result on standard output. So this is a sample which you should do yourself, and I give some hints here about what to do. For step 3, you have to distribute the value of n, the number of strips you want to use, to all tasks which you have read from the standard input on process 0. So you send np minus 1 cents of n. You have to send operations in task 0, and in all other tasks 1 to np minus 1, you have to receive this value, so that every task has knows the number of n. Okay, this it's a syntax, send and receive, we know it by now. Then in every process I start off calculating different strips, namely the strips 1 plus me, and then 1 plus me plus np, and so on, the np's strip on task me. So I do the sum on each process from me plus 1 to n with a stride np. And in this loop, I calculate the function value at the strip, the x value of the strip. Okay, then after doing this local sum, I have to collect the local sums from task 1 to task np minus 1. I have to send them to task 0, and task 0 can then add them all to total approximate value. Okay, this is an exercise for you to do, and you can start with the see. Okay. You can start. The program with the file mpi.f. where I have indicated all these 7 steps, and you just have to complete at some points you have to complete the code. Do this different steps. Okay, this I think you should not do now, but if you have some time, because I want to proceed. And the solution for this parallel program you can find in this directory. Now I want to go one step further, namely, you see the integrand for the quarter circle has different slope in the different intervals. So to get a certain precision in the approximation, you need here only a few strips, but here you would need more strips to get the same precision. So I divide my interval from 0 to 1 to n in intervals, and in every interval I use a different number of strips, and number of strips I use depend on the difference of the function values on the ends of the interval. So the number of intervals in the ice, number of strips in the ice interval is proportional to the total number of strips I will use times the difference of the function values at the border of this interval. So that the total number of strips I will cover will be n as before, but they are distributed in a way that I have more strips in the area where the function varies more faster than in the area where the function varies very slow. And then with the same number of strips, I will get a higher precision as if I would distribute the strips equally over the whole interval. So this is implemented in the program Mpi Precision, where I have a number of intervals with a certain width, 1 over the number of intervals, say 10 intervals. And then in each interval, I calculate the left and the right boundary of the interval, the high and the lower value of the boundary, and then I call the numerical approximation starting from the lower to the higher interval and get the approximate value using a total of n strips. And this approximation and this is num up with this approximation is implemented in the way that I first calculate the function value at the lower and the higher boundary of the interval, and then the number of strips I use is proportional to the total number of strips times the difference of the function intervals at the boundaries. And then I do, as before, just sum the value of the function intervals in the middle of the strips and get the approximation for the part of the integral in this interval as 4 times del times approximation. So this is programmed in the example code ppreg.f. And you need also the numup.f as a subroutine. So this is, I compile it, Mpi, I thought, and I run it. Now, run process, because this is not yet parallelized. One 100,000 strips. And how many intervals do I use? Say 100. Okay. And you see the same number of strips. I get a better approximation to pi compared to this one. Not much better, but a little bit better. See what happens if I $100,000. I use only 20 strips. It's even better. Because then the steepest way on the right side of the interval gets a higher number of strips. So compared to here, I get an error which is a factor of 3 better. So it's meaningful to do this varying number of strips in the integration interval. But what does this mean for parallelizing? Now what I have an interval variations of the numup for calculating the approximate integral from this interval of the total interval from of the interval part of the total integration interval from 0 to 1. And now I want to distribute these evaluations of numup to Mpi processes. But of course, the numup all use different values of strips. So the time for evaluate numup, the different intervals will be differ. So I don't know beforehand how long this evaluation of the different intervals will take. So I don't know how to distribute them on the given number of processes. If I distribute them randomly, then it might be that one process get all the intervals which is a high number of strips, so it will take much longer for this process to evaluate its share of intervals than the other ones. So I have an unequal workload, which is not known at runtime. So how do you parallelize such a situation? Okay, that's a typical case for a parallelized strategy, the farmer-worker model. You have a larger number of intervals and number of workers here, number of processes, and you just distribute one interval to every process, and if one process has finished its calculation, it will get the next interval. So somehow you must have some instance, the farmer, who controls the proceeding of the worker, the work in the worker processes. And if a worker is idle, it must get immediately a new piece of work to do. So in principle, you have two kinds of programs: a program for the farmer, say with task ID equal to 0, and all others are workers, task ID larger than 0. Now, the farmer, say the worker, start with the worker part. The result they they calculate is set to 0, and this value is sent immediately to the farmer, so that the farmer knows this worker has completed a result and can receive a new piece of work. So at the beginning, all workers send their ready status to the farmer, and the farmer who reaches at first, the worker who reaches at first, the farmer will get the first piece of work. Then after the send, the worker will receive a work piece from the farmer, and if this work piece has a number larger than the number of intervals we calculate, it can exit because all the work is done. Otherwise, it calculates the result for this work piece, for this number of interval, and send then the result, which is no longer 0, to the farmer. Now the farmer, on the other hand, does a loop over all the number of intervals plus a loop over the number of workers. And number of workers must be included in this this range, because at first place the farmer will receive a result 0, which indicates that the worker is ready. So if the farmer receives a result from any task, will add the result from this worker to the total result, and then it will inquire where does this result come from. So here we use, we need the status structure from the receive function, and can inquire from where did this result come. And this result came from IP worker, and then it can send the next work piece to this worker from where the last result came. That's the way to organize the distribution of unequal workloads to the number of workers. Of course, one thing is not very satisfying. That, of course, is that the farmer has to do relative little work. It only receives data and adds them up, where the real work is done, namely to sum up the strips in the interval, is done by the worker. So the farmer is most of the time idling. But in this framework, it can't be helped. And if the number of workers is large, then you can neglect this overhead. But of course, you could try to do better to make a multi-threaded farmer, so that in his idle time he also can do some work. I don't want to discuss. So let's just see how this works. Let's look in the program more. This is program Mpi Precision Worker.f. So again, you have to set up a certain number of strips, which I have fixed directly here is number of strips is very large, 100 million. And the number of intervals is 10. Is 50, okay. Then I have the worker, which according to the scheme I showed you, sends it's the first approximation, which is 0, sends this value to task 0 to the farmer to indicate that he is ready to work, and then he does a loop and receives a work piece, a number of the interval which has to be calculated next. And of course, if the number of EW is larger than the total number of interval, then no work has to be done. The worker can exit this loop. And then the worker determines the interval by this interval number, and of course it could be just the lower value is just the higher value is IW, the number of interval times the width of the interval, and the lower value is the higher value minus the width. But that would be not very convenient, because then the worker would start with the lower intervals, which are very flat, where the function is flat and the number of strips to be used are small. So these are workpieces with a small workload. So it's better to start on the right side, where the function is steep and where the workload is high for this interval. So it starts with a lower value of 1 minus IW times width and a higher value low plus width. So, and then it calls this approximation for this interval, and it stores its the number of this interval which has been calculated for documentation reasons. And then it sends the result to the farmer. Then it prints out the intervals it had done, which had been stored in this array to document the interval numbers. So, and the farmer just loops over the number of intervals from 1 to number of intervals plus and number of processes minus 1 times the number of workers plus the number of workers, and then it receives the approximation from any source. It doesn't specify the worker from which he wants to receive the result, and then it inquires which worker has sent it by this status argument set of Mpi source, and then it sends the next work piece to this idle worker, to IPW. So now let us Compile this. And run. So I have to use at least at least two processes, one farmer, one worker. Otherwise, if I only have one process, then I only have the farmer and nothing will be done. But at least two processes, and I calculate. Okay, so you see, I have a large number of strips and a very small error only. Here is recorded which interval the worker worked on. So the worker had to work, one worker had to do all the integrals from intervals from 1 to 50. Now if I do it on, and you see the time I needed was 0.3 seconds nearly. Now I use 3 processes, so 2 workers. This result is the same, but now both worker only had a sub value of the intervals to do, and you see the worker 2 got the first interval, and apparently it took some time, and in this time the worker 2 could do interval 2, 3, and 4, and then only the worker 2 was ready to receive the next one. So you see, it was very good to start with the intervals which had many strips and a long execution time. But you see, time has really been halved from 0.29 to 0.14. So it's very very efficient, this parallelization. And now let's go on to 5. So you have 4 workers. It all takes the same time, and it's again a quarter of it's half of this time, because you have doubled the number of workers. And you see here the worker which did the first interval, second interval it takes is the 19th. So in between, all the other intervals could be done by the other workers in between. So this can go on. You can increase the number of workers, but if you increase it I take too much, 8, what happens? Then you have one worker who is occupied all the time with interval 1, and it takes more time than the other workers need for all the other intervals. So it doesn't make sense to increase the number of workers too much if the if one work piece has a very large execution time. This is a very common way to parallel. So there is a question about using more than one cluster. What do you mean? You can use more than one node in a cluster. minus n2 and minus n3, that would be, you would use a total number of 3 processes on 2 nodes. Of course, you can do it, but the Mpi program doesn't know whether you use different nodes or one node. It only works with tasks, and where the tasks are running, it's without consequence. Apart from the consequence that the communication between the tasks might be depend on the situation, on the position of the task in different nodes. But otherwise, you can use any combination of node number and cores per node. In the case I showed you, this is just using the local multi-core node. So you will have only every one node, always one node with the number of cores equal to the number of tasks you start. But if you want to use more than one node, you have to use the Slurm method to the application on the cluster. All my discussion here is, if I speak about processes or tasks, then I don't care about where these tasks are running, whether on cores in one node or on cores in different nodes. Okay, Jonathan Decker has given the answer that you can use multiple nodes also from the front end by asalloc several nodes. Okay, that's one example, but now you could do it in a different way. See, in this case, you started by the worker started the procedure by sending their ready signal to the farmer, and then the farmer gave them something to work. But you could also also is that the worker sends just their task ID to the farmer, and then the farmer sends the workpiece to this idle worker, and and the worker just receives the workpiece and adds locally the workpieces to a local result. Then, after finishing all the pieces, the local pieces, it sends the local result, the add of all local results, the sum of all local results to the farmer. So that would be another method to do it, another organization. And that would be my suggestion for you. Just program this algorithm in this way, that the workers just send their ID to the farmer, and the farmer then sends to them the work to be done. But of course, this would diminish the work for the farmer even more, because the addition of the local results would be done by the worker, not by the farmer. Farmer then only had to add the local results from the workers to a total result. Okay. This finishes my discussion of this simple application of a numerical integration and how to set up a parallel program for this task. Particularly to use this particular method to distribute unequal workloads on a number of processes. Okay. And for today, I will cover now the last piece, that is the introduction of the collective communications. I have to load the slides. Okay, collective operations. Because we have covered the point-to-point communications, and in principle, all the message passing algorithms can be programmed with send-receive operations. So you don't really, in principle, you don't need any more functionality to parallelize a message, distributed memory system. But in many cases, you have patterns of communications which are repeated very often, which are complicated to program. And for these cases, you have the collective operations. So MPI provides some ways to do more complicated patterns of communications with one call. So you don't have to program this every time yourself. And this kind of collective operations have three different types. For example, a barrier, synchronization barrier, or broadcast, or gather and scatter, and reduction operations. I will cover these in turn. But the common property of all collective operations is that all processes in a communicator, all NP processes in a communicator of size MP have to be call this collective communication function. They are all involved, all processes involved. So the picture is the following. If you have, say, 4 processes, different ranks, and then every process has to call a collective operation, and then it can, all processes have to call next collective operation and so on, and the collective operations are all blocking. So you can proceed in any process. You can only proceed if all the other processes have reached this call to this to the common collective operation. This is the case for MPI 1 and MPI 2, and later on MPI 3 also provides non-blocking versions, but I don't cover them here. Another point which is common to all collective operations, that the buffers, the buffers which are involved in distributing the data must have the same size for all processes. Let's see this in later. So we have three different kinds of collective operations. One is where the communication is the sending of from one process to all other processes. Other is of all processes are sending some data to one process. And then we have some where all processes are sending data to all processes. So, for example, the barrier, you have to communicate from all processes to all other processes, because all processes must know that all other processes have reached the same point of in their program. Broadcast, of course, is a green type. They have one process sends data to all other, sends the same data to all other processes. Scatter is the same, but then it sends not the same data, but different data to all other processes. But one process sends its data to different data to different processes. Gather is the inverse, so that all processes send some data, they are collect on one process. All gather is that if these data which are gathered on one process are broadcast to all other processes. So all processes are involved in together, and all to all is a transpose. I will show the pattern of the data structure for this. Then we have the reduce operation, which means that data from all processes are combined with a sum operation by a sum or a maximum or minimum, and the result is stored in one process. So you collect data from all processes and do some operations on them to reduce these values to one final value, to a maximum or a sum or a minimum. And again, this can be then again scattered to all other processes with the all reduce. And you can also scatter the result to different processes. And finally, we have a mixed, which the scan operations, which do some reduction depending on the amount of reduction is depending on the task ID of the process. These are the three main types of collective operations. For the data flow, I like to show here what we have two dimensions. One, the data, different data, and different processes. So if I have one datum in one process, I can broadcast this datum to all other processes. This is a broadcast. We have one source which gives this value and sends this value to all other processes. If you would do it with send receive, you could do it, of course, by just programming for the master process number of sends to all other processes, and all other processes to call a receive operation. But with one with one call to broadcast to broadcast, you can do this operation. And scatter is if you have different data on the master process, the root process, can distribute the different values to different processes. So you can scatter them. If you have 5 data elements and 5 processes, you can distribute them 5 processes. Gather is the reverse. If you have data on different processes, you can collect them and write them in an array in your root process. And all gather is to gather the data in different processes to one process, but you broadcast this result to all other processes, so that all processes have these values present in their memory. All-to-all means that you just complete exchange, transpose in the 2 dimensions data and processes. Let's look a bit more detail in a bit more detail to barrier. What does it mean? If you have time instances, the programs are in a state, for example, that process 0 calls a barrier, and it will stop until, and the other processes are not yet at the point in their programs where the barrier is called. They proceed until they also come to the call to the barrier. And if all processes are in the state where they call the barrier, then every process can continue its work to barrier. It's a very easy calling sequence. You just have to call the barrier and the communicator in which this barrier should be applied. Now, the barrier is usually not needed because also other functions, MPI functions, will affect some synchronization. For example, the blocking, the other collective communications which are also blocking will also imply a barrier behavior, because they only can proceed if all programs have reached the call to this collective communication call. But it's sometimes useful for debugging purposes or for timing. If you want to be sure that at a certain point in the program, all processes are at the same point in time, then you can use a barrier and then time the next part of the program exactly. Now, the broadcast has a syntax. In Fortran, you have to give the address of the buffer, which will receive the broadcast values in every process, and then the count, that's the number of elements, of consecutive elements should be broadcast starting from the buffer address, and the data type, and then you have to give process ID for the root. You say the value of the buffer from which process should be broadcast to the other processes. This is the root. Then the communicator and the arrow. And every process has to call this collective function, MPI broadcast, and it must supply the same value for root and the communicator. But of course, the same size of data have to be communicated, so the data size count times the size of data type must be the same in all processes. So you could, in principle, use different count and data types in different processes, but the count times the size of the data type has to be the same. But it's, in my mind, not useful to use different data types. So before broadcast, you have the data only in the root process, and after you have same data from the root process in all processes at the address of buffer. Now scatter. Again, you have a send buffer, address where the data reside on the root. And you have S count, the number of data to be sent, and the S count is just the amount of elements in one piece of the same color here. So this is the amount of data which are sent to the to each other process. So you have the send buffer, and then you have the receive buffer. You have to give the address where the data should be stored in the respective processes. So you have data being copied from the root memory to the memory of the different place in memory in all processes. If in the root process you will here the root is process 1, the root process will put the second piece of this send buffer into the receive buffer of the root process. So it's important to remember that the S count does not is the count of the total send buffer, but the count of the pieces which are distributed. This is number of elements in the receive buffer. So again, all processes must have the same value for root and communicator, and the data size must be same on all processes. And the S buffer argument is ignored on all non-root processes. Of course, you don't need to know what is happening in other processes at this address. Total size of data scattered is, of course, the number of processes times the data size, send data size. Now the reverse is the gather. The send buffer, you have a send buffer from address in all processes, and you have a number of elements which is the same in all processes, the type, and then they are sent to the receive buffer in the root process. So these are sent to the receive buffer. Again, the S count times the S type, the size of S type must be equal to R count times the size of R type, so that the amount of data you are gathering, total amount of you are gathering, or the amount you are gathering in each section must be equal to the amount you are sending from each process. This is written here, and the total size gathered is then the number of processes times the size of each section you put together. So these are the basic collective operation. Now there are variants of this which are MPI all gather, which is like MPI gather, but all processes receive the result vector. So you don't need a root argument because you will have the gathered data on all processes. There's no difference. All to all, okay, that's just the transpose in this two-dimensional array with the dimension data and processes. Then we have variants which are the vector variants of gather and scatter. And these are variants where the count of elements in different processes can be different. And also the storing of these elements by gathering in the buffer for the in the memory of the root process can be displaced from the starting address by different amounts. This information about the count and the displacements have to be given by some array of counts and an array of displacements. And this array of counts and the array of displacements must be given as argument in the call on all processes. So see how this looks like. For gathering, we have different amounts in the send buffers on every process. And you want to gather all this data in the different processes into one place or into one process, and at places which you can give by the displacements vector, which you can prescribe by the displacement vector. We have one vector which describes the number of elements in every root, and you have a displacement vector which describes the starting address for each data segment in the root memory, starting from the address of the receive buffer. So the coding sequence is you give the address of the send buffer and the number of count. So, and the number of send counts and the S count, of course, is different on each process. So you have for each task ID you can have a different S count. And then you have a receive buffer, which is only relevant on the root process. And then you have a vector of numbers which contains all the count values of all processes and the displacements where this portion should start in the receive buffer in the root process. So these arguments here, counts and displacement, must be equal to on all processes, but the S count, the number of processes to be sent, can be different. But they must be according to the values in the R counts for the different processes. So again, the size must be conform of the thing which are of the data which are sent to the data which are received in the different sections of the receive buffer. And then the block, the data from S buffer from task E will be stored in the root process with the displacement, starting with the displacement I of element from the starting address of the receive buffer. And of course, the values will be ignored on all non-root tasks of the receive buffer, and the receive counts and the displacements will be ignored on all non-root tasks. So the scheduling is just the reverse. Again, you have two arrays of counts and displacements, but now they refer to the send buffer, refers to the different pieces to be sent how many elements they contain, and the displacements where they are located within the memory, starting from the address of starting address of S buffer. And then you have the receive buffer, and here you have to give the count, which is the actual number in every process of the values to be received. So again, R count will be different, can be different in processes, but S counts and displacements, the arrays of the counts and the displacements must be the same on all processes. Of course, you will not use these values of S counts and displacements on the non-root processes because they are relevant only for the root process. This is again number of bytes must conform on all sending and receiving must conform. This is the thing I explained already. Now, we also have in-place variants. The MPI in-place can be given as an argument to the root process if the root data gathered are already in their place. So this would be a situation like this. And you have a root task. Instead of all tasks have to provide as an argument the send buffer, the address of the data to be sent, but the root does not can say MPI in place if the data are already in the place they would be placed if they had been on this in the send buffer. In place is if the data are already in the root process in the correct place. So you have to, you don't have to imply a send buffer argument here, but say in place. Then you avoid the copying. And for all gather, it would be the case if in all processes the relevant things to be gathered are already in the correct place, and you can call the all gather with the MPI in place argument, and then they will be filled with the missing pieces from the other processes. So much for the data exchange, the collective data exchange. Now, the next point is the reduction operation. So why this is reasonable? Because it's often you have an example, you want to add results from on different processes to a total result, say to the sum of these things. And with our collective operations we had so far, we could just say we define a vector, number of elements corresponding to the number of processes, and then we make a MPI gather so that the local result one count, one element, which is just the local result. They will be gathered into a vector where all the results are gathered on the root process. So then you have all the local results in one vector, and then in the root vector you can add up these local results from all the processes to a total result. That would be the implementation of a global reduction with the measures we have already, with the corrective operations we have at hand already with the gather. And these two operations can be combined with the reduction operation. This is the reason, because it occurs rather frequently, then you can do it in one call and can just say you do a reduce. Local results will be reduced with some operations, which is in this case was a sum, but you could all take a minimum or maximum or product as a operation, and you operate on the local results with this operation and get a total result. It's just one call. So this can be generalized, not just to one datum, but to several count of data. So you have a reduction is just you combine the data on all processes with some operator. This operator should be communicative, because you don't know the order in which the reduction will be done over the processes. So you should be able to use any order. So the sum or a maximum is a allowed operation. So DI is the data in process rank I, and this will be the result which will be posted on the root process. And the data can be either a single variable or also a vector of several values. And if the DI are vectors of several values, then the reduction value will also be a vector of the reduction of these individual elements in the different processes. So an example would be the sum or product or maximum, minimum, or also you can use user-defined operations. There are a lot of predefined operations in addition to the maximum, minimum, sum, product, logical operations bitwise. And there's also an operation where you can look for the maximum and minimum, and at the same time you get information where, on which process the maximum value was located. Minimum value was located in which process. So the syntax is you have a send buffer of number of elements, and you have a receive buffer. The receive buffer is only important on the root process. The receive buffer has as many elements as the send buffer in each process, but it's only on the root process. And the result in the receive buffer is just the first element in the receive buffer is just the reduction of the first elements on the different processes, and the second result, the second element of the receive buffer is just the reduction result of the second elements from the different processes. So if you have any number of elements in the send buffer, and then according number of elements in the receive buffer. And all processes, of course, have to supply the same value for count, root, com, and data type, because you do some operations on the numerical operations on the data, so they should be of the same type to them and to add them and so on. Also here we have some variants. We have an all reduce, where the result is returned to all processes, and so you have no root argument. And you can scatter the result of the reduction of the different elements. Reduction of the different elements you can scatter